Today we're setting up a T3 connection right down here in the Homelab. T3 allows for about 44 megabits per second data transfer rates and is also capable of carrying over 600 phone calls over 2 coaxial cables. We'll use a bunch of Cisco 7200 routers to get this done, particularly a very interesting 7201 with a single port adapter slot we can add T3 capabilities to. T3 was an iteration of the famous T1 connection, so we'll dive into the history of why AT&T created T1 and T3 in the first place, and cover some of the fundamentals of how it works behind the scenes. Let's get into it. This is a Cisco 7201 enterprise router. This particular unit was manufactured in March of 2011, but it was originally released on April 30th of 2007, and it would have cost you 24,000 US dollars list price back then. Now, this is a pretty impressive router for the time. It's got a bunch of gigabit interfaces, both RJ45 and SFP. Get your fiber going in there. But what's really interesting is this big slot labeled PA slot 1. This is a slot called a port adapter. It's got a blanking plate in it right now, and 7200 series fans will be very excited right now. Here we've got this guy's older brother. This is a 7206 from the 7200 series. Came out in 1996 and had a very, very long life, especially given that this one, still supporting some of these port adapters. You can see this one's pretty kitted out. Came out all the way in 2007. Folks might recognize this variant. These things are very heavy, by the way. It's the VXR. The VXR was an iteration and improvement on the original 7200 series, and these two combined were the absolute backbone of enterprise networks, ISPs, the internet in the late 90s and well into the 2000s. In fact, the last date of support for this whole 7200 series was September 30th, 2017. This one was built in 2011, so I don't know if because it was newer it had a later date, but 2017 was the date I found for the 7200 series in general. Now, I find this absolutely fascinating because these guys came out in the mid-90s, and over 10 years later, they came out with a single slot port adapter edition with all the gigabit Ethernet built into the chassis, and then you could expand here. We'll talk a little bit about this one. Doesn't support all the cards these older ones do. And in fact, that's a pretty big issue. Some of the really bizarre older cards, like this big ether switch that takes up 2 slots, you can actually pull out the center pin and get double width cards in here, port adapters. This one doesn't work in the VXR. You need an original 7200 series. And so it's sort of the same story as we get more modern. I think a bunch of these cards I have right here just simply won't work in here, but I'll show you what will. The whole reason I pulled this on the bench today to play around is I wanted to mess around with T3. So you probably are familiar with T1, usually the internet if you're my age. So this is a T1 card with 2 ports, 2 T1 ports. It can run at 1.5-ish megabits per second, and that was blazing fast back in the day. And its original purpose was for telephone calls. You can also transport 24 analog telephone calls that get modulated and digitized over the T1 link. You can bring them back out the other end, and we're going to get really into that soon. This is T3. It operates over coax cables. So I've got a couple of these BNC coax cables that I believe are correct. My cables aren't very long, so when we get into this and try to get a T3 connection working later, we'll probably pull out one of those other 7200s I had stacked here. We'll get a local T3 setup going and measure some speeds and stuff. Here's a close-up of that T3 card. It's 2 DS3s. T3 and DS3 can be sort of used interchangeably when you're discussing them. We'll get into that, don't worry. And this thing is 28 T1 lines, essentially, for a total of 44.7-ish megabits per second if you're saturating all of it for your data traffic, or something like 672 phone calls, which I think is mind-blowing. So I was going to do the usual song and dance. We'll get a T3 card in here. We'll hook up this thing to another router. I've got more T3 cards. And we'll get them connected. We'll get some computers on each end and do the whole ping back and forth thing. I don't think we'll deal with the telephone aspect of T3 today, but that will be in future videos. I don't know if I'll ship 600 calls, but we'll do our best. It got me thinking, Why was T1 and T3 even invented in the first place? So they're part of the so-called T carrier family. T1 was the first one, came out in 1962. Let's dive into that. There's plenty of existing coverage on what T1 is and how it works. We'll dive into that a little bit because it's certainly part of the puzzle. But there isn't a lot of coverage on the question, why does T1 even exist in the first place? Pretty much since its inception, the Bell System, which is what AT&T called its conglomerate of different telephone companies, services, and infrastructure, had a serious problem. A single analog telephone requires at least two wires to function. And the Bell System was growing at a staggering rate throughout the 20th century. This was, of course, often solved by throwing more wires at the problem. And the folks at the Bell System got very good at doing that. But as early as 1911, better ways were being devised and put into action. Multiplexing. Simply put, the act of multiplexing is taking many incoming signals or data streams, coming up with a strategy to combine them, and transmitting them over a single medium. For our case, let's imagine two twisted pairs of copper wiring. You do some opposite magic at the other end to split the streams back out into the individual signals. Multiplexing in telephony was invented by George Owen Squire and patented in 1911. Squire brought his multiplexing scheme to AT&T, and the idea wasn't met with much enthusiasm. Nonetheless, AT&T shipped the first commercial implementation of multiplexing in telephony in 1918, and in a public letter written by Theodore N. Vail, president of AT&T at the time, Vail claims AT&T invented multiplexing. There seems to be some debate about just how much Squire's patent influenced what AT&T built in 1918, though in my research, it definitely seems to have heavily influenced what they built. I think there was some tunnel vision on AT&T's part about some short-term problems they were going to have that made the multiplexing Squire proposed not look ideal, and once they got through that, they obviously went full bore on the idea and came out with the first multiplex telephone line in 1918. But I'll leave that debate as an exercise for you, the viewer, to go do your own research on. But regardless, there's some obvious advantages here, namely, way less copper pairs being ran through the ground. To really belabor the point, imagine I've got 5 phone lines going into some neighborhood. This is going to require at least 2, 4, 6, 8, 10 copper wires to transmit these, say, to another town 50 miles away. I don't want to run 10 copper wires. So imagine I have some multiplexing device that can take these 10 lines, multiplex them onto, let's say, 4 wires. This is a T1 port adapter. It's kind of a reasonable example. It's not really how this works. I'm just trying to make a point. So now I've gone from 10 copper wires down to 4. This is a really good thing. This saves space. There's less physical wires I need to run across town, and I can save money doing this. Multiplexing as a concept is all well and good, but in practice it is accomplished by using something called a carrier signal. That's where the carrier in T-carrier comes from. Basically, in our case, the individual voice calls can be modulated onto a carrier signal and transported over a shared medium together, and that's how we accomplish the multiplexing. There are 2 primary types of carrier signals. You can use something called frequency division multiplexing, or FDM, or time division multiplexing, or TDM. Time division multiplexing is what T1 happens to use, and we'll dive into those details in a little bit after we talk about carriers some more. After the original multiplex line, AT&T created many other carrier technologies, typically designated with a letter. A very popular one was N-carrier, which could handle 12 and eventually 24 voice calls on a single transmission medium. They also had L-carrier. It began in the 1940s, and by the mid-1970s was capable of carrying a staggering 108,000 voice calls over 11 coaxial pairs under a single cable sheath. As I learned about all these other carrier technologies that AT&T has, even back to the one in 1918, I kept asking myself, why did they create T1? What place does T1 have in the history of the Bell telephone system? To answer this question, I dug into many Bell System Technical Journal articles and Bell System Practices documents. As a brief aside, we're going to need to talk about Bell System Practices, or BSP documents, and the documentation culture in general at AT&T. AT&T had documentation on nearly literally everything, and these were often in the form of something AT&T called Bell System Practices. From the technical details of something like T1, to the tools that should be used to prune trees, how to install a number 7 wall fixture in 1925, don't forget to use 1-inch number 8 blued wood screws, and even the typesetting requirements for the Bell System Practices documents themselves. There is a Bell System technical reference document from 1975 on how you should typeset a BSP, down to the pica. I think these documents and the names AT&T gave all their products is an incredible insight into the ethos of the company. I just mentioned the number 7 wall fixture. Well, there's also the public telephone sign number 2, a public telephone sign number 8, and so on. AT&T and its manufacturing arm, Western Electric, use these very simple and, in my opinion, fascinating number schemes all the time. I promise this is all at least tangentially related to T1. T1 was, of course, just the first iteration of AT&T's T carrier. They went on with T2, T3, and that's how the numbering scheme went. It's worth reflecting on the naming and documentation culture of AT&T. They had a virtual monopoly, though of course it was driven by the insatiable demand for more and more and more telephones throughout the 20th century. This is my personal interpretation of the facts, so take it with a grain of salt, but it seems to me that they didn't need to come up with clever names. They would just number the thing, T1, T2. They had all this money being funneled into R&D, and these internal pieces of the Bell system were simply just a cog, and they would be improved. So whenever they iterated on something, they just bumped the number up. The Bell system slogan was one policy, one system, universal service. And I do think that's reflected in their naming practices.
It's a good partnership, the Bell system. Yep, we're a monopoly for sure.
We're a monopoly for sure.
Sorry for that tangent. I actually just secretly made this video to discuss BSPs and how AT&T and Western Electric name their things inside the Bell system. But back to T-Carrier. The Bell system had all these incredible carrier systems. Why create another? Well, according to my research, money and distance. Carrier technology was expensive. Here's a quote from a Bell Systems Technical Journal article in April of 1923. Carrier systems are economical only for the longer circuits in the plant. The cost of the terminal equipment is so great that short circuits cannot economically be provided by carrier apparatus. The way the Bell system worked was an interconnected network of COs, or central offices, and other exchanges. Using this Bell telephone system map from July 1st, 1909 as my guide, if I wanted to make a call from Denver to Jefferson, Colorado, some 70 miles away, my call would flow through no fewer than 4 offices. In a densely populated area, some of these central offices might have been just several miles away. And even as carrier technologies advanced, they were still too expensive over shorter distances. Here's a quote from a Bell Systems Technical Journal nearly 30 years later, April 1951. The minimum distance, however, for which carrier can economically replace voice frequency transmission has been limited by the cost of the carrier equipment, the cost of line treatment, the expense of installation and associated job engineering, and the maintenance effort required. And that 1951 article is about N1 carrier, way after and with lots of advancements made upon the original one from 1918. So the Bell system had a problem. They could economically reduce the amount of wires required for long distance, but not for shorter distances between the various COs, maybe even to businesses, and so on. This meant they were running a lot of twisted pair. Enter the development of T-Carrier. In an article titled Early T-Carrier History by Fred Andrews, Andrews being a lead engineer on the T-Carrier project himself, he sums up their goal nicely. Andrews says, I mentioned earlier that the overall goal was to push the economic application of carrier systems down into the low end of the range of circuit lengths, from roughly 20 to 25 miles to the order of 10 miles. So how did they do it? How did they make T-Carrier affordable at the sub 20 mile range while all the other carriers required longer distances to be economically feasible? Well, 2 big reasons. One is the wires themselves. So T1, at least, we'll talk about T3 later. T1, the original iteration of T-Carrier, requires 2 twisted pairs for a total of 4 lines. And these COs I was showing you earlier already had a ton of these lines running between them. T1 can carry 24 phone calls. So in the perfect case, you're using 4 of your existing trunk lines and you're freeing up 22 other pairs for other uses, or in the case of new construction, you might not even need to run them in the first place. The other reason was an economical use of the equipment doing the multiplexing. T-Carrier was digital. The engineers figured out how to use something called pulse code modulation, we'll get into that later, to turn the 24 phone calls that T1 can carry into ones and zeros, binary data going over the T1 line. The other carriers had been analog up until this point, I believe. I believe T-Carrier was the first one. You can do a little research yourself, I guess. One of the goals of the project was to take advantage of the fact that digital equipment was going to get cheaper and cheaper. And this is how, combined with the fact that the wires in the ground were already usable over T1, they were able to reduce the cost and be able to trunk over the carrier at the 10 mile range. We're wrapping up the history portion of our T-Carrier tour. A couple quick dates. AT&T started development in 1956, and the T1 lines came out, I think, in 1962 for both the Bell System internal use, they used it really heavily, as well as public use. And because it was digital, it lived a very long life. I was born in 1988. I remember T1 being the fastest internet I could imagine, blistering 1.5 megabits per second. And the fact that it lived that long life is because it could carry network traffic, because it was digital and not just analog like the prior carriers. So we know why T1 exists. We know why AT&T needed to develop it. Let's talk about how it actually works.
The world of telecommunications is a complex and quickly evolving environment.
Right you are, Ken. Luckily, we have T1, a survival guide. This is actually a really good book. I do recommend it. Buy one for mom. Get one for the kids. The previous guy left me some notes, so that's kind of cool. The stakes must have been a little higher for him. As good as this book is, and it does actually have a brief history of the telecom industry, which is quite useful, it mostly deals with T1 as a data transmission mechanism. Doesn't dive into the phone stuff too much. So we're going to have to start with, what's a phone call? I'm getting tired of making these diagrams on the computer, so we're going to do it the old-fashioned way. No AI slop here, just some good old human slop. We're going to draw a phone call. So a phone call, the phone literally turns your voice into some electronic signals. It might look something like this as you're talking. This is for demonstration. We're just kind of trying to get the core concepts. A phone call might not actually look like that. It turns out the human voice transmitted over a phone call takes somewhere between 0 and 4,000 hertz. Actually, I should say, for the purpose of having a clear enough phone call and not wanting to capture a bunch of extra audio, the phone folks decided 4 kilohertz was good enough. So this is a phone call. That 4,000 number is important. Remember that, because it's going to ladder up into the total transmission capabilities bandwidth of T1. So what we need to do is turn this somehow into ones and zeros going over a T1 digital line. We do this with pulse code modulation. It turns out you can take samples at given steps and with some magic you can turn it into a bit stream, basically. Now, this 4,000 thing is important. There's something called the Nyquist theorem or the sampling theorem, and it states if you need to take an analog signal and sample it down into its bits, zeros and ones, you need to double the frequency in order to carry enough data for the signal to be good when you demodulate it later. So, 8,000 times per second, we're going to take samples. So if this is a second, 2, 3, 4, in every one of these intervals, 8,000 samples of this sound wave are being taken. Each sound wave is 8 bits, so we need to transfer 8,000 bytes per second. There's 8 bits in each byte. Maybe we should, maybe I'll draw that. This is a byte. It has 8 bits. A bit can be 0 or 1. 8 bits in a byte. And each sample is one of these. So we need 8,000 of these every second. So what's that get us? 64,000 bits per second. Don't worry about that. So we're going to need 64,000 of these ones and zeros per second for each phone call, 64 kilobits per second. Remember that number. It's going to come up later. But again, how do we do this 24 times? We've got multiple phone calls, but we can't just combine all these onto the same, few twisted pairs, because all the calls would be, you'd basically hear all the calls at the same time, and you'd have no way to break them back out on the other end. It's quite the drawing. This is where the carrier stuff comes in. You can do something called frequency division multiplexing or time division multiplexing. In frequency division multiplexing, you have a carrier signal with a much higher frequency, let's say, 100,000 worth of bandwidth in the frequency range. You take each phone call and you put it in a different spot. with something called modulation, which I'm not smart enough to explain to you, but that's what's happening. So in the 3-call situation, each call is being put in a single spot, they call them channels, in the carrier wave, and you can break them back out into the individual calls on the other side. This works really well for analog stuff and the prior carriers we discussed in our little history lesson. When we're dealing with digital data, it's my understanding that time division multiplexing works better. Each phone call gets a slot of time in which it can transmit its bits over the carrier wave. So, bringing this all together, I'm using a zip disk as my ruler, by the way. We've got 3 phone calls. These are 4,000 hertz. We know we can modulate them into bytes, samples of bytes, 8,000 of those per second. If we do time division multiplexing, this call is going to get this little space to transmit its bytes. This call is going to get the next one. And of course, our third call is going to get the next space. That's why it's called time division multiplexing. Each of the inputs gets a specific slot of time to transmit its data in. To drive this home here, it just keeps going. So the phone calls are each transmitting their 8-bit samples in their spot in time. The modulator puts them on the line at the right time. There's a very precise clocking that's necessary for this. We'll see that when we actually play with this for real. And then on the other end, the demodulator is taking these bits and forming them back. So I don't know, maybe I can draw that. Let's say that's the first sample byte, that's the second one. It's going to come out like this. Pretend that my squares are bytes, right? So we know that in this time slot, it's phone 1, and we can break it back out over here, and we've transmitted multiple calls over a single carrier, T-carrier transmission system. And of course, there's 24 of those, and you better believe the Bell system had some special names for everything. Shout out to my beautiful wife for letting me raid her highlighter collection. All right, we're almost there. Each of those phone calls, or they could just be purely digital data, running at 64 kilobits per second. We have 24 of them in a T1 line. These are called DS zeros, or digital signal zeros. Now, we combine all of these together into what's called a DS1. This is all the multiplex digital signals running together, and if you put them over the 4 pairs, that's a T1. So I think it's accurate to say the DS1 is traveling over the T1. Because I didn't even talk about, there's a bunch of repeaters and stuff. You can't just run a T1 line like 100 miles. You have to put in repeaters every so often, and that's important to keep the DS1 signal able to travel those distances. Now, if you take 28 of these and combine them together, you get a DS3 or a T3. And so it ladders up. A T3 is a bunch of T1s together, essentially. There's actually T2 in the middle. I think that was more used like internally. I think for public consumption and public facing, we really only ever saw T1 and T3 on our end. All the other T's were internal to the Bell system. Now, this is all actually a lot more complicated than I'm letting on. There's a lot of work that goes into making this happen. Namely, there are frames. So there's all this framing, and there's extra bits called the framing bit dedicated to the beginning of a frame, and there's different types of framing, and there's things called bit robbing where they actually steal one of the sampling bits and use it for other data in the line. And I'm not really going to dive into that because it's sort of like beyond my expertise, and honestly, it's covered. I wasn't joking, this book's really good. But suffice it to say, it's more complicated behind the scenes than just what's going on here. But because it was digital, it had a long life. You didn't have to transport phone calls. You could transport any digital data and combine it for the full bandwidth. And that's why the T-carrier was able to live so long. Well, let's start getting a little hands-on. Back to this guy. I think we'll start it up at first with no port adapters in there and work our way forward. And I also have to say, almost 2 years ago, this was sent by Tony way over in Sweden. His company, Synotio, no sponsor or anything like that, happened to be the first owners of this. They bought it new, and they actually helped ship it over here for me. So a huge thanks to them, all the way from Sweden, guys. Have a little bit of a problem though. Sometime over the last 2 years, I pilfered the compact flash card that was in here, which hosts the operating system, iOS, that these Cisco machines use. So I'm gonna have to refresh my memory on how to properly format a new card. I'm hoping I can do that with this machine. We might have to borrow another one to be able to do that, and we'll get an iOS version on here that should work for us. Okay, I've got the serial console hooked up to my main machine so we can interact with this. I might have turned this on before. It's been so long that I can't remember. I must have been excited about it when I first got it. Pretty interesting piece of equipment. Maybe that was in a Patreon video or something. So the power switch is off. Yeah, okay. Has power now. Let's see how loud this thing is. Oh yeah. That's pretty loud. Hopefully those fans rev down once it thinks everything's cool. We'll see. My camera and microphone weren't on the last 2 minutes. It must have some sort of internal storage because it is running iOS version 15.2. You can see there. I'm trying to remember what this boot parentheses means at the iOS prompt. I have admin or privilege mode access and everything. It appears to have been factory reset. Well, let me go look up what that means. I don't recall. Joe Clark, Cisco employee on the Cisco forums in 2008, says I'm in boot helper or boot mode, and it's there to help upgrade iOS on run from flash devices. This might be a slimmed down version of the OS, and I can't do that much. I'm not sure yet. He says check out config register, and if it's anything other than what mine is. Yeah, the system image is on the boot flash, which seems fine. I think I'm going to want to transfer that to a compact flash card. Can't remember how to do any of this. No. All right, a few minutes of researching later. This is a minimal K-boot version of iOS. We need to get a real version on there. It cannot see any disks because there's no compact flash. I'm pretty sure I'll be able to put a compact flash card in there, format it, and then jump through the hoops of getting this on a network so I can TFTP a version of iOS down. 1 second. So what's going on here is it's got some internal storage and there's a minimal operating system boot image on there basically. And it is to help you facilitate, hopefully, what we're about to do. So found a compact flash card. I didn't look up if this thing can even read 1 gig flash cards. I guess we're about to find out. How do I open this thing? Maybe. Uh-oh, why doesn't that fit? It doesn't like it. There we go. Helps when you put it the right side up. So what we're going to do is actually get this thing on a network. I guess we'll go for Gigabit Ethernet 0, interface 0, and we're going to transfer via TFTP from the retro rack, which is booting up right now. I've got a TFTP server over there. We'll get this thing on the network, and we'll actually be able to transfer an iOS image off the network onto that card. First, we got to boot this back up and figure out how to format that card, though. I'm pretty sure Cisco uses a proprietary file system, so you can't just pop this in your Windows machine or whatever. Let's see. We're getting back in here, and it detected my 1 gig card right here. It says it's in slot 0. That's a good start. Check out this NASA mug. Pretty sweet. Okay, let's do a dir. Oh, iOS. Stop. No, stop. Let's try that again. Dir. It sees the disk just fine. I wonder if we should format it anyway. Yeah, let's just format it. It's done. Okay, so we're good to go here. Now we need to get this thing on the retro rack network. I think it's trying to reach out and boot over the network for some reason. And that's not going to work though. So conf t int. Let's see what we got here. I think I'm in this one. IP add 10.0. I think 120 should be available. I am assigning an IP address to the interface I just plugged my network into. No shut. Let's bring it up. And with any luck, we can ping. Yeah, ooh, never done it this way before. I think I'm plugged into the wrong cable. I was definitely using the wrong cable. This mystery cable on the ground over here is my home network. Now we are plugged into the retro rack for real this time. As you can see, we can now successfully ping the retro rack network. This thing where it's trying to reach out and configure itself over TFTP automatically is actually pretty cool. Yeah, it's trying to like find stuff. I would like to do that someday, but we're going to turn it off for now because it's annoying. I think it's no service config. That should stop now. All right, next step. This is a VM running in the RetroRack, or I should say it has access to the RetroRack network. It's hosting a TFTP server, and I sort of at random chose this iOS version to put on there. It's for the 7200. Looks like it's iOS 15.2. And what we're going to do is transfer this over TFTP to that flash card. My little trick to turn off this auto-config network crap didn't work, so I'll have to look into that later. But we should be able to copy from TFTP to, I guess it was calling it disk 0. And that TFTP server is there. Uh-oh, state that file name precisely. It is this. And we'll give it the same destination name, and let's see if this works. Kind of doesn't look like it's working. Didn't work. Can we talk to that thing? We can. Why can't we TFTP from that thing? I'm going to go do some troubleshooting. I'll be back when I get this working. I think it was because the permissions were locked down on that file, so I hit it with the old... Everyone gets read-write. Let's try that again. Oh yeah. That's what it was. Now it's transferring it. I see the activity light for the compact flash card on the front of the router. This is good. That is done. Let's do dir, and we can see we have an iOS bin, an iOS image sitting in disk 0. I am going to just power cycle the router and see if it's smart enough to look in its one disk, its compact flash disk, and just boot from that. We might have to configure some things to inform it to do that, but just for science, let's see what happens. It is booting back up. Hopefully we see something about not booting into that kboot image. I think it's in the right configuration to do so, but either way, we're past the hard part. We have the image on the compact flash, so we can figure this out. It's taking longer, and I can see the activity indicator on the compact flash card again, so that is a good sign. Yep, we are in. That is the version of iOS that we put on that compact flash card. We now have a real router. This is good, this is good. I think we're good. Now let's see if we can get the T3 card in there. I should have noted this earlier, but this T-carrier stuff I'm doing is really only applicable in North America, so US, Canada, and then I think Japan also used T-carrier. The rest of the world uses E-carrier. So on the top, we've got an E3 serial card. This is just the rest of the world's version of T3, basically. They're slightly different, so they also had E1 versus T1. E1 could have, I think, 32 channels versus our 24, and 2 megabits versus our 1.5 megabit per second. So it's just worth noting that the rest of the world, as usual, did something else. Maybe it's better, maybe it's worse, I have no idea. We're using T3. So let's get this T3 card in here, and despite what some Cisco docs will tell you about the 7200 series, these are not hot swappable. I think there might be like a subset of cards that are, or something. I think I was looking in the documentation that this 2 DS3 card, so we've got 2 T3 lines right here, over BNC coax, is supported in this 7201, and we're about to find out, because if you get like really unsupported, the router won't boot. Otherwise, it'll just complain about, unrecognized port adapters. So this whole thing's going to fall apart pretty quick if this doesn't work. So far, so good. The enabled light on the port adapter is on. I think I saw something I liked there. We'll do like a show inventory in a second. It saw 2 serial lines. I think we can do show in. Let's see here. Module 1, it knows, is a serial 2 T3 port adapter. Now to figure out how to configure this thing. I'll be back. Part of the puzzle, of course, is we need another T3 interface to hook our 7201 up to. Got this 7206 on the bench. I slotted in a single interface DS3 card here. And the idea is we'll put transmit to receive and receive to transmit with my BNC cables. These are 75 ohm coaxial cables with BNC connectors. From my research, this should work. I think most coax is 50 ohms. Maybe that would work over such a short distance. I'm not sure. But the point is, I fired this guy up. He's happy. The interface seems to find this card no problem. We should be able to configure it. So what we'll do is configure this one first, then we'll fire this one back on because it's kind of loud, configure the other end. Okay, this is the VXR router that has the single T3 interface in it, and we are going to configure the serial 3-3/0 interface. The way these 7200s work is the port adapter slot you're in is the first number. So I happen to be in port adapter slot 3, and there's only one interface, so it's the 0th interface. Now, I haven't done this before. We're going to give each T3 interface an IP address on the same network with some other configuration that I'll briefly talk through. So let's do that. We're going to put these on a 10.01 network. This will be IP address 10.01.10. And then we need to give it some encapsulation. This is how the traffic, how do I explain this? We're going to use HDLC. I don't know if the router supports that. PPP would have been a really popular one back in the day as well. It's essentially how the data is structured on the link. And both sides need to know that they're speaking a particular structuring language, if you know the framing that's happening with the bits. I'm not explaining this very well, but we've already dove into too much of this already. This router seems to support HDLC, so we're going to try that. We need to set T3 framing C-bit. Uh-oh. Maybe not. We don't have any T3 commands. I've been given some bad information online. Bear with me. I'm looking at the serial controller for this T3, and what I wanted was C-bit framing. It says that's on. And I also wanted clock source to be the line. So remember when I was showing you that time division multiplexing, one end of the cable needs to be the clock source, and one end of the cable needs to use that source as its clock because they need very precise timing to get the data to each other correctly, right? So we're going to leave this as line, and we might just be okay, might just work. Let's configure that T3 interface again. We might have to upgrade iOS or use a different router, we'll see. Let's bring this no shut, so tell this thing to come up. And I think if we do a show IP int brief, we should see our serial. Yeah, there's a lot of stuff on this router. At any rate, there it is. I think that's okay. Let's fire this guy up, and we're basically going to do the exact same thing, except we're going to set the clock source to internal for this one. So this one will act as the clock source. This will use it. Then we'll hook our BNC cables up and see what happens. I used to think that 7206 came up slow, but this one's like, I don't know, takes 3 times as long. So we are going to configure interface serial, I think it's 1/0. And I'm just curious if those T3 commands even exist, or if I was reading some weird stuff. They don't. I think that was bullshit. Okay, IP add 10.01.20. This will be .20. So we'll get these guys on the same network. We are going to set encapsulation to HDLC again. And I think I need to figure out the clock thing. Let's see if I can do it. There we go. We're doing it without the internet this time. There is a clock command. In iOS, it's great. So you can type something, and then to learn more about what your options are, you just hit the question mark. So we do clock source, and I think it's going to be internal. So this one's going to act as the clock. Let's do a no shut. I'm having a hard time believing this is all this is going to take, but I think if we do a show IP int brief over here, we can see I have assigned an IP to this thing. Kind of scared that it's down, but we'll see what happens when we plug these cables in. So the interface I just configured was this left pair over here. This, of course, has 2 T3 lines. We configured this one. I think the idea is I put receive of this one. This is the receiving end. Oh, come on. There we go. Receive into transmit of this one. There we go. We're seeing some lights down here. That's exciting. And then receive on this one into the transmit of this one. And there we go. I'm seeing a light here as well. Let's see. This is the 7201 we were just configuring, and it says the line protocol on that interface came up. And it thinks it's up. So the question is, can we ping the other side over to no way? It just works. T3, Homelab T3, folks. Amazing. That was so easy. I'm in shock. So, trying to get you a good view of this. There's this receive clock, I think. It says RCLK. That's what's on all the time. Let's see if we can see anything as I ping. Nah, it happens so fast that these lights can't reflect it. Okay. We have a T3 link between these two routers over these coax cables. Incredible. Or at least we can ping so far. I didn't try pinging the other way. So what I'm going to do is, before I forget, I'm going to write out my configuration to these things in case I need to turn them off. And then what we'll do is get some computers on each one. We'll do some speed tests. We should be able to get something like 44 megabits per second between these routers over these coax cables. And for the record, we are able to ping the other way. This is the VXR, the bigger one, and I can ping to the little one. Wow. So yeah, write your configuration out. I kept calling this thing a VXR. It is an original 7200 series before the VXR came out. You can tell because it doesn't say VXR. It's got that old Cisco Systems logo there. Got all of that. This one's pretty old. Anyway, we're going to need to do a little networking. So I think I'm going to get this on the RetroRack network like it was before. And then we'll make a network with this laptop. We'll plug it into one of these fast Ethernet port adapters because that's 100 megabit. So plenty fast for our T3 link, which is kind of funny to think about. And then I'll have to do some routing rules so that this computer can flow through the T3 link and out to the RetroRack. We'll get another computer on the RetroRack and we'll run some iPerf tests and see if we can get something like 44 megabits per second. Every time I power on one of these that I've had sitting on the shelf or whatever and I'm looking at the old configuration, it's like solving a murder mystery, except I was the murderer and I have forgotten. Anyway, one of these is configured to go directly to the RetroRack's router, but I'm not going to do that because all these go to a switch in the RetroRack room. Anyway, I'm going to have a little think about this and I'll come back with what I figured out. Okay, things have gotten a little convoluted, but I think I've got it. This guy is on a network with this switch and this module right here on a 192.168.50 network, just for fun. There are routing rules in this guy to say if you want to reach the RetroRack, which is at 10.0.0.0, go through the T3 link, and finally out this to the RetroRack. Conversely, on the RetroRack router, I've said if you need to get to 192.168.50 network, go through this guy. And so, we are going to ping the RetroRack, and we can see it. So this is actually flowing over the T3 link. Just for full disclosure, this thing is 192.168.50.10. Okay, all that just for what's probably going to be a 20-second iPerf test. Because I breezed through that, I'll show you one detail, example of one of these routing rules. So this guy is 10.0.0.120. Let me show you what it looks like on the RetroRack router. Here we're looking at the console of the RetroRack router, another 7200 series machine. It is a VXR this time. So we can do show IP route, and we can see it's saying if you need to get to 192.168.50, you should go through 10.0.0.120, which is that small router there, and then I have route rules that get us the rest of the way. There's a more sophisticated way to do this, but I just use static routes, so I can actually ping that laptop from the RetroRack. This is a VM on the RetroRack network. We're going to start it up as an iPerf server, and we're going to see what kind of download speeds we can get on the other end. All right, we're going to start an iPerf client. By default, it will test upload. I don't really care about upload, I care about download, so you hit it with the -R. This is that VM we were just looking at running the server. Let's see what kind of speeds we get. Oh, yeah. About 41 megabits per second, almost as advertised. There's going to be overhead. You're never going to get the full speed. That's pretty good. That's T3. This might be one of my favorite, monstrosities I've ever created. This is really cool looking, I must say. A lot of stuff going on in here. But I'm going to turn this off for now because it is so loud. A few notes on where I'd want to take this in future videos. I've got a lot more of these cards, a lot more variants. I've got just an absolute pile of these multi-channel T1 PRI. We didn't even talk about ISDN and PRI and BRI. We'll do that in a future video. Of course, have the E3 serial. I can't promise you I'd ever do E1 or E3. That being said, viewer named Kyle just sent me this interesting one. It's a PAMC8T E1 Plus. Does that mean it can do T1 and E1? I don't know. Got another slightly different T3 card, DS3 card, in the very, exclusive port adapter clamshell. What's this one? It's a multi-channel 2 T3 Plus, apparently. So that could be cool. And then the elephant in the room, I spent a lot of time going over the history of T1 especially, and the fact that it can carry 24 phone calls, and this thing can carry hundreds of phone calls. I'm not really set up with the 7200 series stuff to do telephony. There's not a lot of telephony options when it comes to these port adapters. So I think we're going to have to explore that, at least with T1. We'll get a few phone calls going over a T1, but I think it's going to be different Cisco gear, of which I have no shortage. So we have successfully created a T3 link. We've got some Homelab T3 down here. I'd like to dive into the telephony aspect of T-Carrier, of course. That's part of the piece of it that interests me not the most, but it's obviously a very important factor. I think it's fascinating that because they chose to go digital, like I've said a million times in this video, it had such a lasting effect on the networking industry. This video was a big one. I didn't know a lot about T1. I know a lot about it now. Hopefully that little historical and medium dive was useful to you. This video has taken me a long time. I'm not here to make excuses, but the research was rough. I didn't cite my sources nearly well enough, I'm sure. I haven't finished editing yet, but all of the sources I used from all the images, all the research I did, all the articles I read, those will be linked down below in the description. I want to make sure that people know I wasn't just pulling this out of thin air. I did my best to research this properly. And a huge thanks to my Patreon supporters. That historical section I actually released as an early release to get some fact checking done and see how the pacing went and see what folks thought. So everyone that responded and gave me some feedback, I really appreciate it. This is the first video of 2026. We are really going to get rolling now. I've got lots of ideas, lots of stuff I want to cover, whether it's T-Carrier or otherwise. I had a really good time with these Cisco routers. I spent a lot of time down here just messing around with them off camera. I love the 7200 series of Cisco routers, partially because it was one of the first ones I really cut my teeth on. Several years ago. I wasn't in the industry back then, but I really like these things. So there you go. I hope you enjoyed this video. I had a lot of fun making it, even though it took me forever. So I apologize for that. We'll get a little more consistent in the coming weeks. If you haven't already, please consider subscribing. I'm almost at 70,000 subscribers. And if you'd really like to support the channel, I'm on Patreon. I post early releases of videos like this, behind the scenes, and what I'm tinkering with. You also get access to the Serial Port Discord, where I hang out all the time. Thanks so much for watching. I'll catch you in the next video.